So I just wanted to do a quick shout out to some YouTubers that kind of got me started doing this. And so the one channel that got me like inspired to like start this channel was MPLAB. She showed that you can take a small lab and without a lower budget, and you can make it into something big. So I mean, a shout out to MPLAB. And then there's Tech Ingredients, who showed me that you can go to the top. You can make it go to the top, you know, in quality and structure and originality. I mean, those guys are the top of the line right there. And then there's Dave's Garage. He does some really cool stuff, and he has some great information. I mean, really great information. And Applied Science. Applied Science. This guy, he makes some of the best videos on some of the most complicated. And I mean, if you wanted to duplicate what he was doing, it'd be really hard. I mean, he goes all out, and he really provides really good content. So a shout out to all you guys like that who inspired me to do this. You guys, you're doing wonderful. We appreciate you. All right, so here we are in the lab again. And so previously we discovered there was a problem with the bus transceiver for the data bus that connects our I/O card to the main brain's SRAM. So I guess we should call that the system SRAM, because all the I/O cards are going to share that SRAM. So we discovered there was a problem, and so we did some measurements with the scope, just probed around, checked the signal, the voltage levels, and so that led me to find that I had made a mistake on the schematic. I had tied the ground pin to VDD, and so it couldn't get any kind of voltage drop across the chip to power it. And so that was a problem because of the way the trace went under the chip. So in order to fix that, I had to cut a couple traces and add a couple jumpers and change it in the schematic and the PCB. So that's kind of where we're at. I'm going to show you a quickie on the jumpers I added, and I added the pull-up resistor. That was one of the problems we found. We needed a pull-up resistor on the chip enable line for the SRAM. So I moved that over to main brain so it can pull up the line for all the cards with only one resistor instead of every resistor, one resistor on every card, because that reduces the resistance of the pull-up every time you add a card, so it's not going to be the same with, you know. So we put that on main brain. I'll show you a picture of that. I didn't take you through the soldering. We've done a lot of soldering. So after that, then we're going to take a dive. We got to get prepared for the microcontroller. So we got to get that on board, the microcontroller. We have to get the ICSP on there, the oscillator for the microcontroller, the reset supervisor, and I think that should be the minimum. Maybe we'll throw on the LEDs because we'll probably want some debugging. So we'll put the 8 LEDs on there for the LED port. And then we got, of course, our reset jumper, and we'll add the remainder of our I/O or our address select jumpers. And then that'll probably be this video. I won't take you probably through all the soldering because we've done, like I said, we've done a lot of soldering already. But that's the way it is. There is a lot of soldering. So you should experience that somewhat so you know. And so then, yeah, we'll get set up for, and the next video will probably be diving into the IDE and setting up a project and getting our code set up to initialize our microcontroller. And yeah, that's gonna be that should be a fat video right there too. So that's what we're looking at. So yeah, let me show you what I did for the actual physical fix on the board, and let's get to it. So I got the chip off just like we did before. Exactly. So then I have my burr. My Dremel tool with a burr on it, and we're going to cut those traces down. Hopefully, the smallest burr I got. So come in here. Hopefully not tear shit up too much. Alright, that looks like we got it. And we got to try to get this right here. There we go. Perfect. Alright. Traces are cut. Swab that down. Not too bad. Not too bad. Now in production, you would take some solder mask and touch up this little part right here that I hit into the ground plane here, just because that's the standard, you know, production standards are higher than for our prototype, but we don't care about that right now. This is a prototype, folks. It's going to be ugly. Alright, so I'll put the chip back on. You guys don't need to see that. And we're rolling right here. Okay, so I put the chip back on after we cut the trace. And then I added a jumper for the ground, connect it to the ground plane. So that looks like this right here. A little bit ugly under the microscope, but not too bad. Something like that. So that's not too bad. So that's what we got. So I had to add a jumper from VCC, from pin 20 to VCC to get that, because where we cut the one jumper that isolated it. And here's the resistor I added on main brain. That's our pull up. And there's our chip right there. That's our SRAM. Okay. Do some probing here. So what we want to check is to make sure we have our VC or VDD to this pin over here. And we do. And we have a good ground here. Yeah. So let's see what we got. Our jumper on here. So our jumper, it's deselected. So this chip should not be active. Let's see what pin 1 is, just for fun. I gotta let you guys see it. Do pin 1, and it's low. Okay. And so then we'll check this at one of our data. Okay, so let's get our probe on here, our resistor probe. All right. Okay, so let's hit one of those data bus points, and that's pulling it high. So this side is in high impedance state. All right. Let's see, what about this guy right here? This is the input of the chip. And it is high. What is it normally? Low. So it's in high impedance. So that chip is disabled. Perfect. Okay. So now we want to change our jumper here to address 0, which selects the chip. Okay. And do the same thing. So first we'll look at what the data bus is naturally. It's low, same before. All right. Nothing new there. So then let's do our pull up on there and see if it is high impedance. And it is, because it went high, it stayed high. Okay. So that probably means that it is in the direction of reading this side over here and writing on the microcontroller side over here. So let's check this one. That would make this an output, and that's low. Okay, so let's see, and that matches over here what we have on the data side over here. So let's see if it's high impedance, and it is not. It is driving towards that way, and that's fine. That passes test. So our fix is good. Okay, so our fix worked, so we're ready to move on to the other one. So let me summarize real fast what happened. So first of all, I didn't put a pull-up resistor on the chip enable line for the system SRAM. So it was, what happened there is, as soon as you turned on the power, then it was active. So it would start driving the bus, and with the data, start driving the data bus. And that would cause a bus conflict with the other cards if any other card was trying to drive the bus at the same time. So the fix for that is adding a 10K pull-up resistor on main brain so it can pull up the line that goes to all of the cards with one resistor. So that fixes that. So when you power it up, then the default state of the SRAM on the peripheral side is deactivated. It's a high on the chip enable. That deactivates the chip, puts it in power down mode actually, but the chip is disabled. So all the inputs and outputs, the address lines, everything is high impedance state. Okay, so that fixes that issue. But then I messed up on the schematic, so the ground pin for our bus transceiver, the 74 AC1 or 245 chip, the ground pin was connected to VCC or VDD. So there was no ground potential or no voltage drop across the chip so that could actually work. It just was kind of floating there at VDD level. And so that's why the signal, all the signals coming out of it were pulled high, because that's all they know is VDD at that point. And that was confusing because it didn't work the way the logic works. And the logic just can't work without ground. So So the fix there was we had to take the chip off the board, cut the trace under the board that connected VCC or VDD and ground together, put the chip back on, and cut the trace for the ground that was still connected to VDD. And so that isolated the ground. So then we ran a jumper from the ground to the ground plane, and that took care of that. But then we had to run another jumper to pull the VDD for the chip, connect it to VDD, because we disconnected it with that second cut. So, and then we did a test, and it passed the test. So everything is good. Physically, logically, our front end is ready for the next step. And the next step is we're going to put on the microcontroller, and we're going to put on the ICSP, and we'll see how long that takes in the video, in video time. And if it's not a full video, then we will start getting into microchip MPLAB IDE and how to set up a project and attaching our microcontroller to it and getting some hello world code put in it. All right, well, let's get to it. So I just went ahead and soldered on the microcontroller because you guys seen a lot of soldering already, and it doesn't fit under the microscope, the whole thing. So we'll solder on, I'll show you soldering on like the oscillator and some stuff. Maybe the rest of the stuff, there's not too many more parts. We'll just knock that out next time or something. And then I did this ICSP, so we're all ready to go on that. Okay, so I increased the scale of my display so it's a little bit bigger. So we'll see if you guys can, if it helps you guys see it better. If not, I'll go a little bit more. I'm at 175% right now. It starts looking funky when it gets too big. So anyway, at this point, I'm assuming that you have downloaded MPLAB from the microchip site and you've installed it to your satisfaction. And so I'll click on it right here. I'm going to pin it to my taskbar while I'm there. And so this is what you should see. This is like, oh, you'll see a start screen and stuff, and you can click, there's an option you can click to like not show that at startup. And there's two screens that shows, but you know, you don't have to do those. But you should see something kind of like this over here. There's no projects. So we have to create a project for our I/O card. So the only thing we need to know right now before we can do it is we need to know the microcontroller that we're using. So I don't think I ever specified the exact one. It's the one I use on my motion board, and it's a DSP actually. They call it a DSPIC at Microchip. So here's the data sheet for it, and you can download this from the Microchip website, or I'll put it in the public folder under the I/O card, so you can download it there if you want. So here's the data sheet. It's a DSPIC 33 family, CK. There's different ones. CK designates a subfamily. And 33 designates that it's a 32-bit, or actually it doesn't. It designates it as a DSP, but it's actually a 16-bit microcontroller. And 512 MP608, that determines how much flash memory it has and the package. It's an 80-pin quad flat package. So it gives you all the things that it has in here. You'll get familiar with some of this stuff. It runs on 3.6 volts, of course. It would be bad if it didn't. Bad for us. And it has 32-bit multiply, and it does some pretty good stuff because it's a DSP, so it's going to have a lot of math stuff. It has different options. All microcontrollers have a different oscillators options. We're going to use the external option, but they have built-in oscillators so that if your oscillator fails, it'll at least boot up. It only runs at 8 megahertz, but it'll actually work. It won't be dead in the water. And it also tells you when a clock failure occurs, if one does. So it shows you what the applications it can be in, and it has some timers, and it has the ADC, 12-bit ADC, which is nice. 24 channels, depending on the package. It has a digital to analog converter. That's one thing that I've really wanted. And so it has some built-in comparators that you can use. It has some UARTs for communication. We probably won't use that in this case. DMA. It has a quadrature encoder for BLDC motors for the encoder. And that's why I chose it for my motion board, because it has that built in. You don't have to have a special chip or try to bit bang it or program it yourself. It makes it really easy. And then, of course, the in-circuit debugging and the JTAG. Safety feature seems to be a big thing these days. You can lock people out of your code so they can't like copy it and stuff like that. Different speed startup. But we're not being too concerned with that right now. So we come down here and it gives what the different ones are and different packages. It comes in a 48 pin and it comes in a 64 pin, and we're using the 80 pin. I like lots of pins because I like lots of options, even though we might be able to go down in pin count if you wanted to save money. That's only like a $5 processor, so I don't really care about that personally. So then you should get familiar with the data sheet, because when you design a circuit with a microcontroller, you got to know a lot of different things about it. You have to get to know it intimately. And you will, if you get it working and you write code for it, you will know this microcontroller. So there's a block diagram of all the things it has and this and that, but we're not going to get into that quite yet. So let's go back to MPLAB. And so we want to create a new project, right? So file, new project. It's going to be a microchip embedded, an application project. Click next. Now you got to pick, you can pick just your family of microcontrollers, but you can just do this right here and pick it individually. You have to anyway. So it's kind of in alphabetical order. So you want to do a DSP. I guess it isn't completely alphabetical, is it? So we got a DSP IC 33 CK 512608, right? So then the tool, you will have to have, that's another thing I kind of should have mentioned, you'd have to have the tool, the programming tool, okay? So if you jump over here and you go microchip snap, it's the cheapest. And there's a tutorial here too. But if you go to, you can buy it directly from Microchip too. Or you can look for it on Mauser, DigiKey, eBay. You can even get Chinese knockoffs. I actually have one. One of my other PICs is a Chinese knockoff. So this one, the Snap, is actually cheaper than I even thought. This is from Europe though, but It's supposed to be, but that's kind of interesting. I might have, because I have my VPN on it, doesn't know where I'm at, maybe. But that's pretty cheap. I mean, 15 euros is what, 20 bucks or something like that. So yeah, it's pretty good. And then they have it all set up to where how you can use it, and different stuff like that, and user's guide and stuff. So you can get it pretty cheap. So you'll need that too. So then you'll pick your tool. I'm using the PIC Kit 4 right at the moment. And you don't have to choose that right at the moment either. You can choose it later. So I have this one already downloaded. XC16 is for this chip, this microcontroller, because it's a 16-bit chip. Unlike MainBrain, which is a 32-bit chip, so it uses a different compiler. So you're going to name your project. So I'm naming it I/O board. Very original. And you could do like version 1 or whatever you want. And then you got to tell it where to put it. Now I keep mine on a separate drive. And now the reason I try to keep all my working files on a separate drive is because if my system crashes and I have to reformat my C drive, then I don't wipe out all my work that I've worked on for the last however many years, right? So I keep it on a different drive. And you might even want to use a cloud backup too, which I don't. So then we have that's under project. Oh, no, that is not what I wanted. We got to go back. You have to be careful because if you double click on it, I'm in project, but I want to do I/O board. So this is the directory you want. All right. So that's my directory, and it puts in its own little thing here, and you can do this, use project location as the folder. But if you do that, it can freak things out, but it works fine. We'll get into that later, because I like to do that. I don't like their add-on thing. And set it as the main project. All right, so then finish. All right, so here you are. It gives you your microcontroller here, and it's going to give you some status about it, some statistics later. So we don't have any files. So basically for C, you're going to want to create a header file for your globals and your declaration of your functions. So let's create a new file, and it's going to be a C file, and it's going to be a header file, and we're going to call it I/O board H. The extension's automatic. All right, and that's where we want it, and everything's good there. So let's finish. All right, so it creates this header file, and it doesn't put it in yet. Oh yeah, it did. I don't know why it put it under important files. I would say remove it from the project right now. All right, so then just take and save it. It looks like it's already saved, okay? So then we can come up here to header files, add existing item, and I/O board H. All right, so, and it doesn't matter where it is in there, but I just like to have my header files under the header file thing. All right, so then for here, you can put your little header for your file, however you want to do it. I'll put my name here. Whoops. And it says when it's created. I just like to put 2025. And I'll change this later. I go a little more in depth. But see, I don't really want any of this stuff in here, right? Well, I want this. I don't want the C++ part. So we can take this part out, all the C++. And all this does here, if it's already defined in a file, it doesn't like try to put it in again because it'll freak out the compiler and give you an error. So this just like if you already defined something in here and it's already been called by another file, it won't call it again and trigger an error. All right, so that's our basic thing right here for our header for right now. So let's save that. And then we're going to come back over here and create a new file because we got to create our main C file. So we want a new file. It's going to be a C file, C source, and next. And we'll keep it same name, IO board. Okay, and the .c. So we can save it same place, same name, just has a different extension. All right, so that's this, right? So then you can put your header in however you want to put your name in, and you got to say whatever you want to say by using comments. And so comments, I used green last time, but as long as it's just 2 forward slashes, it's a comment. So we can just say this is file name, colon, IO board.c. Okay. All right. And so now we're going to get into some code. And so every C program has to have a main, and it has to return an integer. But it can be void here. All right. So that's going to be our main code. All right. So you can check it right here. You can just go up to the project, right click, clean and build, huh? Oh, that's what I forgot. All right. Forgot about that. We got to add our source files here. We haven't done that. This doesn't really matter. This is kind of a way to keep track of it. But in here, it matters. So we have to add an existing item, and we get to add our IO board C. So now this is in there. It calls, that's what we're going to compile right here. So any files we put under source files gets compiled into one file that becomes your firmware. So now that we have that in there, let's compile it. All right, build successful. Loading completed. All right, so we're good. All right. So then, we don't have to go any farther to plug in to our microcontroller. So let's go back to the bench and we'll plug in our microcontroller and we'll see if we can connect and everything's okay with that. Okay, so here we are. We're ready to plug in our programmer to our card and see if it works. And I haven't tried it yet, so I don't know. The only thing I did is I powered it up to make sure it didn't like pop. So let's take our, and we got our microchip deal here, our programmer, EIC kit 4, and so the way the ICSP connector always is for our boards is the red wire always goes close to this reset jumper over here. So it goes on like this, I do believe. Okay. Now we're plugged in. Now let's plug in main brain. Make sure nothing gets hot. All right, no smoke. We're looking good. Okay, so let's go back to our code. And so now that we're plugged in, then we should be able to program nothing, our nothing code. We should be able to like connect to the microcontroller. So we can do that. Just hit this right here, and we'll see if we can connect to the programmer and everything. So it's trying to get connected to the programmer. And so we're good. It found our chip right here. So it programmed nothing. So we're connected to the PIC kit 4. And this is like the code in there. It's firmware. Target voltage detected. And that's our 3.3 volts on the board. The target device is our device. Very good. Device revision and device ID and some other stuff, right? So we're good. We are ready to write some code. So now we got to start setting up the microcontroller. So that, my friends, is probably the end of this video. And in the next video, we're going to get down into some C code and writing some, I guess you'd call it device driver code for our microcontroller. Maybe you could call it bootstrap too. I don't know. But it's the very bottom line code that we're going to start writing. And we're going to start toggling some of these lines that we were testing by hand. So we're going to get the scope on there, and we're going to toggle them and write to them, and we're going to do some stuff. So that's our plan. And I'll see you in the next video.